Hello everyone, good morning. This is Kusaraju. Currently, I am pursuing my Masters in Signal Processing and Communication at IIT Tirupati. Now, I am going to give you a presentation on the first real-time face detector. The real-time because of its ability to detect the faces rapidly. It implemented on a conventional 700 MHz Intel Pentium 3 on approximately 300 by 300 image. It detected the faces at 15 frames per second. Such a algorithm is given by this paper titled Rapid Object Detection using a boosted cascade of simple features. These are the authors of the paper, Viola and Michael Jones, which is published in the Journal of Computer Vision and Pattern Recognition in the year of 2001, about 20 years ago. So far it has the 20,000 plus citations. The goal of the paper is detecting the objects in an image or in the sequence of images, which is a video. Why this object detection is utmost important is the features that it has. Suppose take surveillance systems which are associated with activity recognition. These will be useful in law enforcement, for example. Let's take an example of the social distancing, whether it is maintained or not in many corners of the city or any places. So everywhere we can't put personal to check it. So some places they are using drones. Even they are using drones. For each drone, every visuals we can't check manually. So there if we have that object detection followed by this activity recognition, it will be quicker than autonomous driving. In autonomous driving, the car has to know what are there around it to take a decision, what to do in the next, what are the objects that are there, any other cars, pedestrians, buildings like that, and medical imaging, guided image diagnosis, image searching to the web through the image of our interest, ball tracking, object tracking, like that. In that all these applications, the basic step is detecting the object followed by something, that procedure. That's why object detection becomes utmost important. Here the method presented is comes under machine learning approach, where we have to extract the features and give it to a trained classifier to get the class of the object. Whereas in deep learning approaches, the end-to-end process is done by neural networks. Here, the Viola-Jones algorithm can be trained to detect a variety of object classes. It is demonstrated and partly it is motivated by the task of face detection, whether the object is face or not, like a binary classifier. It has three steps in the method. The first one is evaluation of R-like features. Then reducing the number of features which are irrelevant through the AdaBoost algorithm and training the classifier also. Then to make it quicker, come up with a cascade structure of the classifier. Let's get into each one by one. The first one is evaluation of R-like features. The R-like is the name because of its due to similarity with R wavelets using rectangular functions. Here they use mainly three kinds of rectangular features, that are 2 rectangle features, 3 rectangle features, 4 rectangle features. There is a common saying that in the world there are 7 people who look exactly like us. It's maybe true, may not be true. Let's keep it aside. But one thing is true, that every human face will share some common properties. Like in the image of the face, the region along the eyes is darker than the region along the upper part of the cheeks, and the region of the bridge of the nose is brighter than the region of the eyes. Taking this basic idea, they come up with the features. In this, the feature value is subtraction of sum of the pixels which lie in this white region from the sum of the pixels which are lie in the shaded region. In this process, the two in this two rectangle in the each box, each square with the different scales, 1 cross 1, 2 cross 2, like that, in different scales, that will be features will be evaluated. But the 24 by 24 window which fits that it will be made to pass through entire image. In that each subsection of the image, these are rectangle features. In that each rectangle feature, different scales. So all this sum of the pixels doing all that for different scales, it is time expensive, time consuming. So to make it quicker, they come up with a new representation of the image, which is integral image. The value at each location of the integral image is found out by going to the exact location in the original image, finding the sum of the pixels which are lie left and top of that location, including the pixel at that location. Let's take an example. Here it is shown. Let's take this location in the integral image. Now we want to find out, going to the same location in the original image, sum of the pixels which are lie left and top of the image, including this pixel 3 plus 3 plus 6 plus 8, which is 20. In this way, all these values will be evaluated. Now, finding the sum of the pixels in any scales of the square box, a rectangular box, which is here it is easy. Easy in the sense constant time in any of the square, that sum of the pixels will be calculated. How it is using these integral image values in the corresponding square box. Using that 4 corner references, we can find out the sum of the all number of pixels within that box. So here it is shown. Let's take it is the image and it is a detection window. Say let's say we are finding the 4 by 4 rectangle feature. Here we have to find the sum of the pixels in the region D, which is the 4 corner references, 4 plus 1 minus 2 plus 3, which is sum. Here it is shown the example. We want to find the sum of the pixels in this region, which is 4 plus 9 plus 1 plus 8, which is given by this A plus C minus B plus D here. Then constructing the classifier, which is AdaBoost, which is short for adaptive boosting. A 24 by 24 detection window. In that window subsection of the image, there are 180,000 rectangular features we will get in the subsection of the image, which are far larger than the image pixels, which are 576. In the all features, many of the features are irrelevant. So to remove that irrelevant ones and to train the classifier, they used the adaptive boosting algorithm. What it does, how it eliminates the irrelevant ones is, how we say they are something is irrelevant is, take a two rectangle feature in this 24 by 24 window, this two rectangle feature will be calculated at different locations. At only this location, it will give a high value. In the different location, if you take any other location, it won't give such a high value, because here only it has that dark region in this region, this shaded one, and brighter one in this one. So if you take any to this two return feature at different location, it will be smaller than this one. So which won't give any information like classification. Here it can somewhat say yes, it might be phase like that. So such each feature could called as weak classifier. Remaining all will be rejected. So combining all these weak classifiers into a strong classifier, the ensemble of these things, AdaBoost algorithm takes care of all these things. These are the two features that are selected by AdaBoost algorithm. Next one, combining the classifiers in a cascade structure. Why it is needed is that 1,80,000 features that come in a window that are very larger. So that are reduced to say 2000 like that by AdaBoost. But in the each window in the image a 24 by 24 each window, it might not have the faces. So but going to all the 2000 features and end up with the decision of there is no face, it is a time consuming waste of time. So to reject such a windows as earlier as possible, so they come up with the cascade structure. Here in each stage, it has some 10 features like that. If that window satisfies these 10 features, then only it will go to further processing, saying that it might be phase. It will be evaluated next other stages. Otherwise, it will be rejected. This is what cascade structure, like it is decision tree. One by one it goes. If it is true, then go to next stage. If it is false, rejected. True, goes to next stage. If it goes to all stages, then it will be evaluated like it is a phase. It is combined cascade structure form. These are the results. So here we can see that each 24 by 24 window detected some faces in the entire image. Here we can see some faces are not detected. Here some non-faces are detected as faces. It is false negative. A face which is detected as non-face is false negative. It is false positive. A non-face detected as a face, but it has the high accuracy and high quicker process compared to the other models. Then that's why it is implemented real time. It's become first real time face detector. These are the receiver operating characteristics curve of the classifier. The ROC curve shows the ability of the binary classifier. It is a graphical plot plotted the true positive versus false positive as the threshold is varying. The true positive rate is taken along y-axis, which is also known as detection rate. The false positives rate, here false positives are taken in number rather rate. The false positives are taken around the x-axis. It is shown the accuracy. around at a false 40 false positives, around it is giving 90% accuracy. It is all done on MIT plus CMU test set. Here the step size 1 means we are sliding that detection window 24 by 24 detection window on the image. By 1 pixel it will be slided over the image. Here this step size 1 means that. These are some references that are given in the paper. The Harlech features first used in this paper, which is a general framework for object detection. Later, those ones are adopted by Viola and Jones. Then second paper about some boosting, like these are some references given there. The most of the content in the presentation are taken from that Viola and Jones paper. Some of the content from internet. Thank you.